right now, at this very moment while you are watching this video, there is a small spacecraft, no bigger than a compact car, hurtling through the absolute darkness of interstellar space at a speed of 61,000 kilometers per hour. It has been travelling without stopping, without slowing down, without any fuel pushing it forward, for more than 46 years. It left Earth in 1977, back when there were no cell phones, no internet, no personal computers. And yet, this tiny machine, built with technology less powerful than the cheapest calculator you can buy today, is still alive, still sending whispers back to Earth, faint, impossibly weak signals that take more than 22 hours to reach us, travelling at the speed of light. That spacecraft is Voyager 1. And here is the part that should keep you awake tonight. Despite travelling for nearly half a century, despite covering more than 24 billion kilometres, despite being the farthest human-made object from Earth in all of history, Voyager 1 has barely left our cosmic driveway. It has not even made it to the end of our street. In the grand scale of the universe, it has moved less than a grain of sand on an endless beach. Today, we are going to take a journey. Not just the journey of Voyager, but a journey into the nature of space itself, into the terrifying, beautiful, and mind-bending reality of just how big the universe actually is. We are going to explore what Voyager discovered out there in the dark. We are going to understand why quantum physics governs the very signals that keep Voyager connected to us. We are going to confront the uncomfortable truth about human exploration and what it means that our greatest achievement in space travel amounts to barely a single step in a journey of 1 billion miles. But first, let me ask you something. When I say Voyager has travelled 24 billion kilometres, what does that number mean to you? Can you picture it? Can your brain actually hold that distance? Let me try something. If you got into a car right now and started driving at highway speed, 100 kilometers per hour, never stopping, never sleeping, just driving through space in a straight line, it would take you more than 27,000 years to reach where Voyager is right now. 27,000 years. Human civilization itself is only about 10,000 years old, so you would need to drive for nearly 3 times the entire length of recorded human history just to catch up to this one small spacecraft. And yet, that enormous distance, that incomprehensible number, is nothing. It is cosmically insignificant. The nearest star to our Sun, a small red dwarf called Proxima Centauri, is 4.2 light-years away. Voyager 1, after 46 years of non-stop travel, has covered roughly 0.0006 light-years. Let me say that again, 0.0006. That is 6/10,000ths of a single light-year. If the distance to the nearest star were a marathon, Voyager has not completed the first metre. It has barely lifted its foot off the starting line. This is the reality of space. This is what we are going to explore today. And I promise you, by the end of this video, the way you think about the universe, about distance, about time, about our place in all of it, will never be the same again. Before we go deeper, I want to share something with you, something that happened recently that almost nobody talks about, but it reveals the extraordinary emotional connection between humanity and this tiny distant machine. In November of 2023, something went wrong with Voyager 1. The spacecraft, which had been faithfully sending scientific data back to Earth for over 4 decades, suddenly started transmitting gibberish. The data made no sense. The telemetry was garbled. The flight data system, the computer responsible for packaging scientific and engineering data before transmission, had malfunctioned. For the engineers at NASA's Jet Propulsion Laboratory in Pasadena, California, this was a crisis unlike any they had faced before. Think about what they were dealing with. This spacecraft is so far away that any command they send takes 22.5 hours to arrive. Then they have to wait another 22.5 hours for the response. That is a 45-hour round trip for a single exchange. You cannot troubleshoot in real time. You cannot reboot the system and watch what happens. Every single attempt at a fix requires nearly 2 full days just to see if it worked. The engineers began a painstaking investigation. They sent a command called a poke, essentially asking the flight data system to try different sequences and report back what it found in its memory. Weeks passed, then months. November turned to December, December turned to January, January turned to February. Still gibberish. The world's attention moved on to other things. But inside JPL, a small team of engineers, some of whom had been working on Voyager since before many of us were born, refused to give up. In March of 2024, after analysing the garbled returns, they identified the problem. A single chip in the flight data system memory had failed. One tiny piece of hardware, probably smaller than your fingernail, corrupted by decades of exposure to cosmic radiation in interstellar space. That one chip was making the entire system produce unusable data. But here is the beautiful part. They could not replace the chip. They could not send a repair crew 24 billion kilometers into space. So instead, they had to find a way to work around it. They needed to relocate the affected code to other parts of the memory, scattered in small sections across what little functional space remained. On April 20th, 2024, they sent a command that would move a portion of the flight data system code to a new location in memory. Then they waited, 22.5 hours for the signal to arrive, another 22.5 hours for the response. And then, for the first time in 5 months, Voyager 1 spoke clearly again. The data made sense. The engineering readouts were correct. The team at JPL, some of them in tears, knew their spacecraft was back. Think about what this means. A machine launched in 1977, carrying a computer with 69 kilobytes of memory, less than the memory needed to store a single modern photograph, was saved by engineers who had to work blind across a 45-hour communication delay, diagnosing a chip failure from 24 billion kilometers away. This is one of the greatest feats of remote engineering in human history. And almost nobody knows about it. This is the kind of story that defines the Voyager mission. Not just the science, not just the discoveries, but the human determination behind it. The refusal to let go, the love, if we can call it that, between a species and its most distant creation. Now let me take you back to where it all began, back to why Voyager exists in the first place. In the early 1960s, an aerospace engineer named Gary Flandreau was working at JPL on trajectory calculations. He was studying the outer planets, Jupiter, Saturn, Uranus and Neptune, looking at their orbital positions over the coming decades. And he discovered something remarkable. In the late 1970s, roughly 1976 to 1978, all 4 giant planets would be arranged in a geometric alignment that occurs only once every 175 years. This alignment meant that a spacecraft launched at the right time could use the gravity of each planet to sling itself to the next one, like a ball bouncing off a series of walls, each bounce adding speed and changing direction toward the next target. This maneuver is called a gravitational slingshot, or gravity assist. Without it, reaching Neptune would require a flight time of 30 years or more, and enormous amounts of fuel. With it, a spacecraft could visit all 4 giant planets in a single 12-year mission. The opportunity would not come again until the year 2150. Nobody alive today would see another chance like this. NASA recognized the significance. They began planning what was originally called the Grand Tour. Budget cuts eventually scaled back the mission, and what emerged were 2 spacecraft, Voyager 1 and Voyager 2, each designed for a minimum 5-year mission to Jupiter and Saturn. But the engineers built them to last. They built them better than they needed to. And that decision, that quiet act of engineering excellence, is why we are still talking about Voyager nearly 50 years later. Voyager 2 launched first, on August 20th, 1977. Voyager 1 launched 16 days later, on September 5th, 1977. Despite launching second, Voyager 1 was placed on a faster trajectory and would arrive at Jupiter first. Both spacecraft carried identical instruments for studying planetary atmospheres, magnetic fields, moons, and rings. And both carried something else. Something that had nothing to do with science. Attached to the side of each Voyager spacecraft is a golden phonograph record, a 12-inch gold-plated copper disc containing sounds and images selected to represent the diversity of life and culture on Earth. This was Carl Sagan's idea. Sagan, the famous astronomer and science communicator, chaired the committee that decided what would go on the record. It contains greetings in 55 languages. It contains music from Bach, Beethoven, Chuck Berry, traditional songs from around the world. It contains the sound of waves, wind, thunder, birds, whales. It contains brainwaves of a woman in love. It contains 116 images encoded in analog format, showing everything from human anatomy to mathematical equations to photographs of Earth. The golden record is a message in a bottle, thrown into the cosmic ocean. The chances of any alien civilization ever finding it are essentially zero. The spacecraft will drift through interstellar space for millions, perhaps billions of years, and the space between stars is so phenomenally empty that the odds of Voyager passing close to another star system are almost non-existent. But that was not really the point. The golden record was a statement about who we are, a species that looks up at the stars and says, "We are here. We exist, we think, we feel, we make music, we love." Let us now talk about what Voyager actually found when it reached the outer planets. Because the discoveries it made transformed our understanding of the solar system in ways nobody predicted. Voyager 1 arrived at Jupiter in March 1979, and immediately everything we thought we knew about the largest planet was challenged. Jupiter's atmosphere was far more complex and violent than expected. The Great Red Spot, which we had observed from Earth for centuries, was revealed to be a storm larger than the entire Earth, with winds exceeding 600 kilometers per hour. And it had been raging for at least 300 years. But it was not Jupiter itself that delivered the biggest surprises. It was the moons. Jupiter has many moons, but 4 of them, discovered by Galileo in 1610, are large enough to be worlds in their own right. Io, Europa, Ganymede, and Callisto. Voyager turned its cameras to these moons, and what it found was staggering. Io, the innermost of the 4 large moons, was covered in volcanoes. Not dead volcanoes, active ones. Voyager captured images of volcanic eruptions in progress, plumes of material shooting hundreds of kilometers above the surface. This was the first time active volcanism had been confirmed anywhere in the solar system other than Earth. And the mechanism was entirely unexpected. Io is not heated by radioactive decay the way Earth's interior is. It is heated by tidal forces, the gravitational squeezing and stretching caused by Jupiter's immense gravity and the orbital resonance with the other moons. Io is essentially being kneaded like dough by gravitational forces, and that mechanical energy is converted into heat, making it the most volcanically active body in the entire solar system. Then there was Europa. Smaller than our own moon, Europa appeared in Voyager's images as a smooth, icy world, crisscrossed by long dark lines. The surface was remarkably flat, with almost no craters, which immediately told scientists something extraordinary. A lack of craters means a young surface. If there are no impact craters, it means the surface is being renewed, recycled, replaced, and the only way an icy surface gets replaced is if there is liquid water beneath it. Europa, scientists realized, almost certainly harbours a global ocean of liquid water beneath its frozen shell. And where there is liquid water, there might be life. This single discovery suggested by Voyager's images and confirmed by later missions, opened up an entirely new field of astrobiology. Before Europa, we thought life could only exist in the habitable zone, that narrow band around a star where temperatures allow liquid water on the surface. But Europa showed us that liquid water, and potentially life, could exist far from any star's warmth. Heated instead by tidal forces, this expanded the possible locations for life in the universe by an almost immeasurable factor. Every icy moon in every star system suddenly became a candidate. Voyager 1 then moved on to Saturn, arriving in November 1980. Saturn's rings, which through telescopes appeared as a few broad bands, were revealed to be made of thousands upon thousands of individual ringlets, a complexity that no model had predicted. The rings contained gaps, waves, braids, spokes, and other structures that kept scientists busy for years trying to explain. Voyager discovered new moons embedded within the rings, tiny shepherd moons whose gravity sculpted the ring edges into sharp boundaries. And Saturn had its own moon surprise. Titan, Saturn's largest moon, was revealed to have a thick, opaque atmosphere, denser than Earth's atmosphere, composed primarily of nitrogen with complex organic chemistry occurring in its upper layers. You could not see the surface through the orange haze. But the atmospheric chemistry was producing compounds similar to those thought to have existed on early Earth before life began. Titan was essentially a frozen laboratory of prebiotic chemistry, a window into what Earth might have looked like 4 billion years ago. After Saturn, Voyager 1's primary mission was technically complete. But its trajectory, designed to give it a close flyby of Titan, had sent it out of the plane of the solar system. It could not visit any more planets. Voyager 2, however, was on a different path. It continued on to Uranus, arriving in January 1986, and then to Neptune, arriving in August 1989. These encounters provided humanity's only close-up views of these distant ice giants, views we have not repeated to this day. Voyager 2 remains the only spacecraft to have visited Uranus and Neptune. At Uranus, Voyager 2 found a planet tipped on its side. Its rotational axis tilted 98 degrees, essentially rolling around the Sun like a ball rather than spinning like a top. Its magnetic field was tilted 60 degrees from its rotational axis and offset from the planet's centre, unlike anything seen elsewhere. Its moons displayed bizarre geology, including Miranda, a small moon that looked like it had been shattered and reassembled, with cliffs 10 times higher than the Grand Canyon. At Neptune, Voyager 2 found the fastest winds in the solar system, over 2,000 kilometers per hour, on a planet so far from the Sun that it receives 900 times less solar energy than Earth. Where was the energy driving those winds coming from? This remains one of the unsolved mysteries of planetary science. Neptune also revealed a large dark spot similar to Jupiter's Great Red Spot, though it later disappeared. And Neptune's moon Triton was found to be volcanically active, erupting geysers of nitrogen gas, despite surface temperatures of negative 235 degrees Celsius. Every single encounter at every planet produced discoveries that nobody anticipated. This is the nature of exploration. You go somewhere new, and the universe tells you things you did not know to ask about. But there is one more image from Voyager's planetary encounters that deserves special attention. On February 14, 1990, as Voyager 1 was speeding away from the solar system, having completed its encounters with Jupiter and Saturn years earlier, Carl Sagan persuaded NASA to turn the spacecraft around and take one final photograph of Earth. From a distance of 6 billion kilometers, Earth appeared as a tiny dot, less than a single pixel in size, suspended in a scattered ray of sunlight. Sagan called it the pale blue dot. His words about that image are among the most profound ever written about our place in the cosmos. "Look again at that dot," he wrote. "That is here, that is home, that is us. On it everyone you love, everyone you know, everyone you ever heard of, Every human being who ever was lived out their lives. Every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, every hopeful child, every inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. That image, that pale blue dot, was taken from 6 billion kilometres. Voyager has since travelled 4 times farther, and it is still, as we said, barely out of the driveway. Let that sink in. Now, if you are finding this journey as fascinating as I think you are, take a moment to hit that subscribe button and the bell icon. We are about to go much deeper into the science of how Voyager communicates across impossible distances, how quantum physics makes it all possible, and why the true scale of space is something that should fundamentally change how you think about everything. Drop a comment below telling me how far you think Voyager will get before it finally goes silent. I read every comment, and I find the discussions in the comments section of these videos to be some of the most thoughtful conversations happening anywhere on the internet. Let us continue. After its encounter with Neptune in 1989, Voyager 2 joined Voyager 1 in what NASA calls the Voyager Interstellar mission. The goal was no longer to study planets. The goal was to study the boundary between our solar system and interstellar space, to find the edge of the sun's influence and cross it. To leave home. But what does it mean to leave the solar system? This is more complicated than it sounds. Our solar system does not have a clean, sharp edge. It has layers, like an onion, each one marking a different kind of boundary. The sun is constantly blowing a stream of charged particles outward in all directions. This is called the solar wind. These particles, mostly protons and electrons, race outward at hundreds of kilometers per second, creating a bubble around the sun called the heliosphere. Inside this bubble, the sun's influence dominates. The magnetic field is solar, the particles are solar. It is, in a very real sense, the sun's territory. But the sun is not alone. Our solar system is moving through the local interstellar medium, the thin gas and dust that fills the space between stars. As the solar wind pushes outward, it eventually meets the interstellar medium pushing inward. There is a region where the solar wind starts to slow down as it collides with interstellar material. This region is called the termination shock. Voyager 1 crossed the termination shock in December 2004 at a distance of about 94 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun, about 150 million kilometers. So the termination shock was 94 times farther from the Sun than Earth is. Beyond the termination shock is a turbulent region called the heliosheath, where the solar wind piles up and becomes denser and hotter as it collides with interstellar material. This is a chaotic, dynamic boundary region. Voyager 1 spent 8 years crossing it. Then, on August 25, 2012, something remarkable happened. Voyager 1's instruments detected a sudden, dramatic change in its environment. The density of solar particles dropped by a factor of more than 1,000. The density of interstellar particles, galactic cosmic rays, jumped sharply. The magnetic field changed its orientation. Voyager 1 had crossed the heliopause, the outer boundary of the heliosphere. It had entered interstellar space. It became the first human-made object to do so. Voyager 2 crossed the heliopause 6 years later, on November 5, 2018, at a distance of about 119 astronomical units. The data from this second crossing was in some ways more valuable than the first, because Voyager 2 still had a working plasma science instrument that Voyager 1 had lost decades earlier. This allowed scientists to directly measure the temperature, density and speed of both the solar wind and the interstellar plasma right at the boundary. What did they find? The interstellar medium is not empty. It is not silent. It is a thin but measurable soup of atoms, mostly hydrogen, along with cosmic rays, magnetic fields and dust. And it hums. In 2021, scientists analysed Voyager 1's plasma wave data and detected a faint, persistent hum in the interstellar plasma. This is the sound of the universe between the stars. Not silence. A hum, the gentle vibration of particles in the vast emptiness, like the low drone of a tuning fork that has been ringing since the birth of the galaxy. But here is the critical point that brings us back to our central theme. Crossing the heliopause, entering interstellar space, is often described in media coverage as leaving the solar system. But this is misleading. The heliosphere is just one boundary. The sun's gravitational influence extends far, far beyond it. And this brings us to the Oort cloud. The Oort cloud is a theoretical sphere of icy objects that surrounds our solar system at enormous distances. It is thought to be the source of long-period comets, those comets that take thousands or millions of years to complete a single orbit around the sun. The inner edge of the Oort cloud is estimated to begin at roughly 2,000 to 5,000 astronomical units from the sun. The outer edge may extend to 50,000 or even 100,000 astronomical units. 100,000 astronomical units is about 1.6 light-years. The nearest star is 4.2 light-years away. Voyager 1, right now, is at approximately 164 astronomical units from the Sun. The Oort cloud begins at 2,000 astronomical units at the very minimum. Voyager has not even reached the front door of the Oort cloud. And the Oort cloud extends for tens of thousands of astronomical units beyond that. At its current speed, Voyager 1 will not reach the inner edge of the Oort cloud for roughly 300 years. It will not exit the Oort cloud for about 30,000 years. 30,000 years. 30,000 years from now, Voyager 1, assuming it still exists as a physical object and has not been destroyed by a micrometeorite or eroded to nothing by cosmic radiation, will finally emerge from the outer edge of the Sun's gravitational realm. Only then can we truly say it has left the solar system, and after 30,000 years of travel, it will still be nowhere near any other star. The nearest star, Proxima Centauri, is not even in the direction Voyager is heading. Voyager 1 is heading generally toward the constellation Ophiuchus. In about 40,000 years, it will pass within 1.6 light-years of a star called Gliese 445. It will not come particularly close. It will simply drift by, in the dark, in silence. Let me now try to give you a sense of this scale in a way that your brain might actually grasp. Because numbers alone do not work. Our minds evolved to understand distances we can walk or run. Kilometers are manageable. Thousands of kilometers we can sort of grasp. But billions of kilometers? Light years? These are not real to our intuition. We need analogies. Imagine the sun is a basketball. A standard basketball about 24 centimeters in diameter. On this scale, the Earth would be a tiny grain of sand, about 2 millimeters wide, located 26 meters away from the basketball. Jupiter would be about the size of a marble, 135 meters away. Neptune, a slightly smaller marble, would be 800 meters away. Half a mile from the basketball representing the Sun, you would find the last major planet. On this scale, where is Voyager 1? About 3.5 kilometers away from the basketball. That sounds far, right? A 30-minute walk from the Sun. But where is the nearest star? The nearest star, on this scale where the Sun is a basketball, would be another basketball sitting approximately 6,800 kilometers away. From New York to London, you have a basketball in New York, another basketball in London, and Voyager has walked 3.5 kilometers from the one in New York. 3.5 kilometers out of 6,800, that is barely leaving your neighborhood. That is stepping out your front door. That is quite literally barely leaving the driveway. And this is just the nearest star. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. The galaxy is 100,000 light-years across. And there are 2 trillion galaxies in the observable universe. The observable universe is 93 billion light-years in diameter. These are numbers that have no meaning to the human mind. They are beyond comprehension. We can write them down, but we cannot feel them. This is the fundamental problem of space exploration. Not engineering. Not money. Not politics. Distance. The sheer, crushing, incomprehensible distance between everything and everything else. Space is called space for a reason. It is almost entirely empty. And the empty parts are staggeringly, heartbreakingly large. Now I want to take you into a realm that might seem unrelated at first, but is actually fundamental to everything Voyager does. Quantum physics. The science of the incredibly small. And I am going to show you how it connects directly to the Voyager mission, to deep space communication, and to the very nature of the universe Voyager is travelling through. Let us start with something basic but profound. How does Voyager communicate with Earth? How do we receive signals from a spacecraft 24 billion kilometers away? Voyager carries a radio transmitter. This transmitter sends signals back to Earth using a 23-watt radio beam. 23 watts. That is less than the power of a refrigerator light bulb. A typical household light bulb uses 60 watts. Voyager's entire transmission power is about the same as a dim night light, and this feeble signal has to cross 24 billion kilometers of empty space before reaching the antennas of NASA's Deep Space Network on Earth. By the time that signal arrives, it is phenomenally weak. The power received by the Deep Space Network antennas from Voyager is approximately 10 to the minus 16 watts. That is a decimal point followed by 15 zeros and then a 1. It is 1/10 quadrillionth of a watt. This is less energy than the impact of a single snowflake falling on your hand. It is less energy than would be produced by a single bacterium in its entire lifetime. And yet, we can detect it. We can extract meaningful data from it. How? This is where quantum physics enters the picture. To understand how we can detect such an impossibly faint signal, we need to understand something about the nature of light and radio waves. In 1900, Max Planck proposed something radical. He suggested that energy is not continuous, but comes in discrete packets, which he called quanta. A single packet of electromagnetic energy is called a photon. Radio waves, just like visible light, just like X-rays, are made of photons. Each photon carries a specific amount of energy determined by its frequency. The higher the frequency, the more energy per photon. Voyager transmits at a frequency of about 8.4 GHz in the X-band radio spectrum. At this frequency, each individual photon carries an incredibly tiny amount of energy, roughly 5.6 times 10 to the minus 24 joules. These photons leave Voyager's antenna and travel across the solar system at the speed of light. As they spread out over 24 billion kilometers, the photons become enormously spread out. The number arriving at Earth's antennas per second is extremely small. But here is the quantum reality. Each photon that does arrive carries information. Each photon is a discrete unit of the electromagnetic field. It either arrives or it does not. There is no half a photon. This is the quantum nature of reality asserting itself across billions of kilometers. The communication between Voyager and Earth is, at its most fundamental level, a quantum phenomenon. We are counting individual photons, extracting bits of information from discrete quantum packets of energy. The Deep Space Network uses some of the most sensitive receivers ever built. These receivers must distinguish the genuine photons from Voyager from all the other sources of radio noise, thermal noise from the receiver electronics, cosmic microwave background radiation. radio noise from the Earth's atmosphere. The fundamental limit on how sensitive these receivers can be is set by quantum mechanics itself. There is a noise floor, a minimum level of uncertainty imposed by the Heisenberg uncertainty principle. The Heisenberg uncertainty principle tells us that there is a fundamental limit to how precisely we can know certain pairs of physical properties simultaneously. For electromagnetic signals, this means there is always a minimum amount of noise that cannot be eliminated, no matter how perfect our technology becomes. This is called the quantum noise limit, or shot noise limit. It is not a limitation of our engineering, it is a limitation of nature itself. The remarkable thing is that the Deep Space Network operates very close to this quantum limit. After decades of engineering refinement, the receivers used to detect Voyager's signal are almost as sensitive as the laws of physics allow. We have essentially reached the point where the only thing preventing us from detecting even weaker signals is the fundamental quantum structure of reality. Let me go deeper into this. When we talk about the signal from Voyager being detected, what is actually happening at the quantum level is extraordinary. The antenna collects electromagnetic waves, but those waves are made of discrete photons. The receiver must amplify these photons without adding too much noise. The first stage of amplification in the Deep Space Network receivers uses devices called masers, which stands for microwave amplification by stimulated emission of radiation. Masers are the microwave equivalent of lasers, and they work on pure quantum mechanical principles. In a maser, the incoming signal photons stimulate the emission of additional identical photons from atoms that have been pumped into an excited energy state. This amplification process is coherent, meaning the new photons are perfect copies of the incoming signal photons. They have the same frequency, the same phase, the same direction. This is a quantum phenomenon. It relies on the quantum mechanical process of stimulated emission, first described by Einstein in 1917. So here we have a direct, practical, essential quantum connection to Voyager. Without quantum mechanics, without the maser, without the discrete nature of photons, without stimulated emission, we could not hear Voyager. The very fact that we are still in contact with a spacecraft 24 billion kilometers away is a triumph of quantum physics applied to engineering. But there is another quantum connection to Voyager that goes even deeper. Voyager's power source. Voyager does not run on solar panels. At the distances Voyager operates, the sun is too faint for solar power. Instead, Voyager is powered by 3 radioisotope thermoelectric generators, or RTGs. These devices convert the heat produced by the radioactive decay of plutonium-238 into electricity through the thermoelectric effect. Radioactive decay is a purely quantum mechanical process. It cannot be explained by classical physics. When a plutonium-238 atom decays, it emits an alpha particle, which is a helium nucleus consisting of 2 protons and 2 neutrons. But the alpha particle is initially trapped inside the nucleus by the strong nuclear force, which creates an energy barrier around the nucleus. Classically, the alpha particle does not have enough energy to escape over this barrier. It is like a ball trapped in a valley between 2 hills, without enough speed to roll over either hill. And yet, it escapes. It escapes through one of the strangest phenomena in all of quantum physics. Quantum tunneling. In quantum mechanics, particles do not have a definite position. They have a probability wave function that describes where they might be found. The wave function does not stop at the energy barrier. It extends through it, decaying exponentially but never reaching zero. This means there is always a small but non-zero probability of the alpha particle being found on the other side of the barrier, and occasionally that probability manifests. The alpha particle simply appears on the other side, as if it had tunneled through the barrier. It never goes over the barrier. It never breaks through the barrier. It simply appears on the other side. This is not a metaphor. This is not an approximation. This is literally what happens. The alpha particle quantum tunnels out of the nucleus. This happens at a statistically predictable rate, which is why we can calculate half-lives. Plutonium-238 has a half-life of 87.7 years, meaning half of the atoms in a sample will have tunneled their alpha particles out in that time. The rate of tunneling depends on the height and width of the barrier and the mass and energy of the particle. For plutonium-238, this rate gives us the steady heat that powers Voyager. So think about this. Every watt of electrical power that keeps Voyager alive, that powers its instruments, that feeds its transmitter, that sends those 23 watts of radio signal across the void, ultimately comes from quantum tunneling. Without quantum tunneling, plutonium would not decay. Without decay, there would be no heat. Without heat, there would be no electricity. Without electricity, Voyager would be dead. Quantum tunneling keeps Voyager alive. There is something almost poetic about this. The smallest phenomenon in physics, quantum tunneling at the scale of atomic nuclei, is what enables us to explore the largest scales, the interstellar distances that Voyager is crossing. The quantum and the cosmic are not separate. They are intimately, inescapably connected. Let us go further into quantum territory. There is a question that people often ask about deep space communication. Could we use quantum entanglement to communicate with spacecraft instantaneously, without the speed of light delay? Voyager's signals take 22.5 hours to reach Earth. Could quantum entanglement eliminate this delay? This is a fascinating question, and the answer is important because it reveals something deep about the nature of quantum mechanics and the structure of reality. Quantum entanglement is real. It has been experimentally confirmed beyond any doubt. When two particles are entangled, they share a quantum state such that measuring one particle instantly determines the state of the other, regardless of the distance between them. Einstein famously called this spooky action at a distance. If you entangle two photons and send one to Voyager and keep one on Earth, then measuring the Earth photon will instantly collapse the wave function of the Voyager photon. This correlation is instantaneous, appearing to violate the speed of light. This has been experimentally verified. The correlation is real, and it does appear to be instantaneous. So why can we not use this for communication? Why can we not send messages faster than light using entanglement? The answer is subtle and beautiful. When you measure an entangled particle, you get a random result. You might get spin up or spin down, with equal probability. You cannot control which result you get, so you cannot encode a message in the result. The person on the other end also gets a random result. From their perspective, their measurements look completely random. There is no way for them to tell, just by looking at their particles, whether you have measured yours or not. The correlations only become apparent when you compare the two sets of measurements side by side, and to compare them, you need to send that comparison using a classical communication channel, which is limited to the speed of light. So the information itself cannot travel faster than light. Only the correlation is instantaneous, and the correlation alone carries no usable information. This is known as the no communication theorem in quantum mechanics. It is not an engineering limitation. It is a fundamental law of nature. Quantum entanglement cannot be used to send information faster than light. Period. The universe has a speed limit, and it enforces it absolutely. This might seem disappointing, but it is actually profound. It tells us something deep about the relationship between information and reality. The correlations in entanglement are real. They are non-local, but they cannot carry messages. The universe allows non-local correlations while simultaneously forbidding non-local communication. This is a subtle distinction that took physicists decades to fully appreciate, and it reveals that the structure of reality is more nuanced than either pure locality or pure non-locality. It is something in between, something strange, something quantum. So no, we cannot use quantum entanglement to talk to Voyager instantly. We are stuck with the speed of light. And for Voyager, that means a 45-hour round trip for any conversation. This is the loneliness of interstellar space. This is the isolation that deepens with every kilometre Voyager travels. But quantum physics does offer potential improvements to deep space communication, just not through entanglement. Quantum communication protocols, using techniques like quantum key distribution and quantum error correction, could potentially allow us to extract more information from fewer photons, effectively making future deep space communication more efficient. Quantum receivers, which use the quantum properties of light more cleverly than classical receivers, could potentially exceed the sensitivity of even the best masers. Research in this area is ongoing, and while it would not eliminate the speed of light delay, it could allow us to maintain communication with spacecraft at even greater distances than Voyager. There is another quantum aspect of Voyager's journey through interstellar space that deserves attention. The vacuum of space itself. When we say space is empty, we are speaking classically. Quantum mechanically, empty space is not empty. The vacuum, according to quantum field theory, is a seething foam of virtual particles. Pairs of particles and antiparticles are constantly popping into existence and annihilating each other, too quickly to be directly observed, but with real, measurable effects. This is called vacuum fluctuation, or zero-point energy. The energy of the quantum vacuum is not zero. Even in the most perfect emptiness, at absolute zero temperature, with no particles or radiation present, the vacuum still has energy. The electromagnetic field still fluctuates. Virtual photons still appear and disappear. The vacuum is alive with quantum activity. One measurable consequence of this is the Casimir effect. If you place two very thin metal plates extremely close together in a vacuum, they will be pushed toward each other by a tiny but measurable force. This happens because the vacuum fluctuations between the plates are restricted, fewer virtual photons can exist in the narrow gap, while outside the plates all wavelengths are present. The imbalance in radiation pressure pushes the plates together. This has been measured to high precision and agrees with quantum predictions. Voyager is travelling through this quantum vacuum. The interstellar medium through which Voyager moves is incredibly sparse, roughly 1 atom per cubic centimetre on average. But the quantum vacuum is everywhere, even in the space between those atoms. The vacuum energy fills all of space uniformly. It is the lowest possible energy state of the universe, and it is not zero. In fact, the quantum vacuum energy is one of the deepest mysteries in all of physics. When physicists calculate the expected energy density of the vacuum using quantum field theory, they get a number that is roughly 120 orders of magnitude larger than what is actually observed. This is sometimes called the vacuum catastrophe, and it is the largest disagreement between theory and observation in the history of science. We do not know why the predicted vacuum energy is so much larger than the actual vacuum energy. This remains an open problem, and its resolution might require a completely new understanding of quantum gravity. The vacuum through which Voyager travels is thus not just emptiness, it is a quantum mystery filled with energy that we do not fully understand, governed by laws that we have not yet fully discovered. Voyager is sailing through a sea we have barely begun to comprehend. Let me now bring us to another profound aspect of quantum physics that connects to the Voyager story. The measurement problem. The question of what quantum mechanics actually means. When a photon leaves Voyager's antenna and travels 24 billion kilometers to Earth, what is it during the journey? Is it a particle following a definite path through space? Is it a wave spreading out in all directions? Quantum mechanics gives us a strange answer. It is neither, until we measure it. According to the standard interpretation of quantum mechanics, the Copenhagen interpretation, the photon exists in a superposition of states during its journey. It does not have a definite position. It does not follow a definite path. It is described by a wave function that spreads out through space, representing the probability of finding the photon in any given location. Only when it interacts with the deep space network antenna, only when it is absorbed and measured, does it take on a definite state. This raises profound questions. Does the photon exist during its 22-hour journey from Voyager to Earth? What does exist mean for a quantum particle in transit? Is the wave function real, an actual physical thing spreading through space? Or is it merely a mathematical tool for calculating probabilities? These are not just philosophical questions. They have practical implications. Different interpretations of quantum mechanics make the same predictions for all experiments, but they differ in what they say about the nature of reality between measurements. The Copenhagen interpretation says the question is meaningless. There is no reality between measurements. The many worlds interpretation says the photon takes all possible paths simultaneously, in different branches of reality. The pilot wave interpretation says the photon has a definite position guided by a real wave. We do not know which interpretation is correct. We may never know, since they all make identical predictions for any experiment we can perform. But the question matters for our understanding of what the universe is actually like. And every photon that arrives at Earth from Voyager, every faint whisper that crosses the void, is a tiny quantum mystery, a packet of energy that has traversed billions of kilometers in a quantum state we do not fully understand. Now let me take you into the future. What happens to Voyager from here? Voyager's power supply is slowly dying. The plutonium-238 in its RTGs decays steadily, losing about 4 watts of electrical power per year. When Voyager launched in 1977, its RTGs produced about 470 watts of electrical power. As of now, they produce less than 200 watts. This is not enough to power all instruments simultaneously, so NASA has been systematically shutting down instruments one by one over the years. By approximately 2025 to 2030, there will not be enough power to operate any scientific instruments at all. The last instrument to be shut down will likely be the plasma science instrument or the magnetometer. At some point after that, there will not be enough power to transmit a signal back to Earth. On that day, Voyager will fall silent. It will send its last photon toward Earth, and then nothing. The engineers at JPL will listen. They will point the Deep Space Network antennas toward Voyager and listen. And they will hear nothing. Just the quantum noise of the vacuum, the hiss of cosmic microwave background radiation. But no signal from Voyager. On that day, humanity will lose contact with its most distant creation, and it will never get it back. But Voyager will not stop. It will not slow down. There is nothing in interstellar space to slow it down. No friction, no drag, no resistance. Newton's first law will carry Voyager forward at 61,000 kilometers per hour, forever, long after all its instruments are dead, long after its transmitter has gone cold, long after its plutonium has completely decayed, long after the gold anodized aluminum covers of its golden records have turned dark. Voyager will drift, through the interstellar medium, through the Oort cloud, out of the solar system entirely, into the space between the stars. It will drift for millions of years, hundreds of millions of years. The sun will exhaust its hydrogen fuel and swell into a red giant swallowing Mercury, Venus, possibly Earth. It will shed its outer layers and collapse into a white dwarf, and Voyager will still be drifting. In about 300,000 years, Voyager 2 will pass within about 4 light-years of Sirius, the brightest star in our sky. In about 40,000 years, Voyager 1 will pass within about 1.6 light-years of Gliese 445, a dim red dwarf in the constellation Camelopardalis. It will not stop. It will not enter orbit. It will pass by, silent and cold, carrying its golden record with greetings in 55 languages, carrying Chuck Berry and Beethoven and the sound of a mother kissing her child. The probability of any intelligent being ever finding Voyager is effectively zero. Space is too vast, the distance is too great, the density of stars too low. Voyager could drift for the entire remaining lifetime of the universe, trillions upon trillions of years, and never come close enough to anything for anyone to notice it. And yet, we sent it. Knowing this. Knowing the odds. Knowing that the golden record would almost certainly never be played by alien ears. We sent it anyway, because the act of sending mattered. The statement mattered. We are here. We exist. We reached out. Now I want to take a step back and think about what Voyager tells us about the nature of scientific exploration itself. Because there is a pattern here that I think is deeply important. When Voyager was designed in the early 1970s, nobody knew what it would find. Nobody predicted the volcanoes of Io. Nobody predicted the ocean of Europa. Nobody predicted the complexity of Saturn's rings. Nobody predicted the nitrogen geysers of Triton. Nobody predicted the sounds of interstellar space. Every single major discovery was a surprise. Every single one overturned existing theories or revealed something entirely new. This is the argument for exploration. Not just space exploration, but scientific exploration of all kinds. You cannot predict what you will find. If you could predict it, you would not need to go. The entire point is that reality is more complex, more surprising, more creative than our imaginations. Every time we look somewhere new, with instruments more sensitive than before, we find things we never expected. This is also the story of quantum physics. When scientists first began probing the atomic world in the early 20th century, they expected to find tiny versions of classical objects, tiny solar systems, tiny billiard balls. Instead, they found superposition, entanglement, tunneling, wave function collapse, uncertainty. They found a reality so strange that Einstein refused to fully accept it until his death. A reality where particles can be in two places at once, where observation creates reality, where the future is not determined but probabilistic. Quantum physics was not predicted, it was discovered, just as Voyager's discoveries were not predicted. The universe does not conform to our expectations, it has its own ideas, and those ideas are always more interesting than ours. Let me now talk about something that is often overlooked in discussions of Voyager and deep space travel, the quantum nature of time itself. As Voyager travels through interstellar space, it experiences time differently than we do on Earth. Not by much. At Voyager's speed of 61,000 kilometers per hour, the relativistic time dilation is negligible. But the principle is important. According to Einstein's special relativity, time is not absolute. It flows at different rates depending on relative velocity. A clock moving at high speed runs slower than a stationary clock. This effect becomes significant only at speeds approaching the speed of light. Voyager travels at about 0.006% of the speed of light, so its clock runs slower than ours by an amount too small to measure. But the principle remains. If Voyager were travelling at 90% of the speed of light, its clock would run at about 44% of the normal rate. Time would slow down dramatically. Now here is where quantum physics intersects with relativity in a way that remains deeply mysterious. In quantum field theory, the combination of quantum mechanics and special relativity, time plays a fundamentally different role than space. In non-relativistic quantum mechanics, time is a parameter, not an observable. You cannot have a time operator the same way you have a position operator. Time flows uniformly, serving as the backdrop against which quantum evolution occurs. But in general relativity, time is dynamic. Time is part of space-time, which curves and bends in the presence of mass and energy. Time flows at different rates at different locations depending on the gravitational field. Near a black hole, time nearly stops. Combining quantum mechanics with general relativity, creating a theory of quantum gravity, is the holy grail of modern physics. We do not have such a theory. String theory is one candidate, loop quantum gravity is another, but neither is complete or experimentally confirmed. We do not know what time is at the most fundamental level. We do not know if time is continuous or discrete, whether there are quanta of time, a minimum possible duration, the way there are quanta of energy. Voyager is travelling through a universe whose deepest nature we do not understand. The space through which it moves, the time through which it endures, the vacuum that surrounds it, these are all quantum mysteries that we have not solved. Voyager is not just exploring interstellar space, it is, in a philosophical sense, exploring the edges of our ignorance. Let me bring up another fascinating connection between Voyager and quantum physics. The concept of decoherence and the classical world. One of the great mysteries of quantum mechanics is why the macroscopic world appears classical. Why do chairs and tables and spacecraft have definite positions and velocities? Why do we never see a basketball in a superposition of two locations? Atoms can be in superposition. Electrons can be in superposition. So why not big things? The answer, according to modern physics, is decoherence. When a quantum system interacts with a large number of environmental particles, its quantum superposition rapidly entangles with the environment. The delicate quantum phases that give rise to interference and superposition get distributed across so many environmental degrees of freedom that they become, for all practical purposes, unobservable. The system appears classical. It appears to have a definite state. Voyager, with its roughly 825 kilograms of mass, is firmly in the classical regime. Its position in space is definite. Its velocity is definite. It does not tunnel through barriers or exist in superposition. Its quantum nature is completely hidden by decoherence with its own internal degrees of freedom and its interaction with the few particles of the interstellar medium. But at the same time, every atom in Voyager is quantum mechanical. Every electron in its circuits obeys quantum rules. The photons it transmits are quantum. The nuclear decay that powers it is quantum. The macroscopic classicality of Voyager emerges from the quantum substrate. It is not that quantum mechanics fails for large objects. It is that quantum mechanics for large objects gives rise to classical behaviour through decoherence. The classical world is a consequence of quantum mechanics, not a contradiction of it. Voyager exists at this beautiful intersection. It is a classical object made of quantum parts, communicating through quantum photons, powered by quantum tunneling, travelling through a quantum vacuum, in a universe whose ultimate nature is quantum. It is a macroscopic ambassador of quantum physics, whether it knows it or not. Now I want to address something that often comes up in discussions about the scale of the universe and our place in it. A feeling of insignificance. If the universe is so vast, if Voyager has barely left the driveway, if we are an infinitesimal speck in an infinite cosmos, does anything we do matter? I want to approach this question scientifically, not philosophically or spiritually, but through the lens of what we know about the physical universe. Here is what science tells us. We are the universe looking at itself. We are made of atoms forged in the cores of stars that exploded billions of years ago. The carbon in our bodies, the iron in our blood, the calcium in our bones, all of it was created inside massive stars through nuclear fusion. When those stars died in supernova explosions, they scattered these elements across space, where they eventually coalesced into new stars, planets. And eventually, us. We are not separate from the universe. We are part of it. We are the part that asks questions. We are the part that builds spacecraft and sends them into the void. We are the part that formulates quantum mechanics and general relativity. We are the universe becoming aware of itself. And this is not nothing. In fact, it might be the most extraordinary thing that has ever happened in the cosmos. As far as we know, consciousness is rare. Complex technological intelligence is extremely rare. We have searched for signs of other civilizations and found nothing. The universe may be full of life, or it may not be. We do not know. But what we do know is that here, on this tiny dot, orbiting an ordinary star in an ordinary galaxy, something remarkable occurred. Matter organized itself into structures complex enough to contemplate its own existence. Voyager is an expression of that. It is not insignificant. It is the opposite of insignificant. It is matter that organized itself to fling a piece of itself into the cosmos, carrying a record of its songs and images and greetings, reaching toward the unknown. That is extraordinary. That is unprecedented as far as we know. The universe spent 13.8 billion years to produce a species that could do this. Whatever that means, it is not nothing. Let me now return to the purely scientific aspects of Voyager's journey and discuss something that I find deeply fascinating. The boundary between the heliosphere and interstellar space turned out to be nothing like what we expected. For decades before Voyager reached the heliopause, scientists had models of what the boundary should look like. The dominant model predicted a relatively clean, sharp boundary where the solar wind abruptly ends and the interstellar medium begins. A cosmic bow shock, similar to the shock wave in front of a supersonic aircraft, was expected to exist ahead of the heliosphere as it plows through the interstellar medium. What Voyager found was much more complex. The boundary region was not clean. It was messy, turbulent, and full of surprises. In 2012, as Voyager 1 approached the heliopause, it entered a region that nobody had predicted. A boundary layer where the solar particles had disappeared, but the magnetic field had not yet rotated to the interstellar orientation. Scientists debated for months whether Voyager had actually crossed into interstellar space, or was in some unexpected intermediate zone. It took detailed analysis of plasma wave data, which could infer the plasma density from oscillations triggered by solar eruptions, to confirm that Voyager 1 had indeed crossed the heliopause. Furthermore, the expected bow shock ahead of the heliosphere was not found. In 2012, scientists using data from the Interstellar Boundary Explorer satellite concluded that the heliosphere is probably not moving fast enough through the interstellar medium to produce a shock. Instead, there is likely a bow wave, a gentler disturbance. This was a direct contradiction of decades of modelling. Voyager 2's crossing in 2018 added more complexity. The heliopause appeared to be at a different distance than where Voyager 1 crossed, suggesting the boundary is not a simple sphere, but a dynamic, asymmetric shape, possibly pushed and pulled by varying conditions in both the solar wind and the interstellar medium. These findings remind us of a fundamental truth about science. Our models are approximations. Reality is always more complex, and the only way to know what is actually out there is to go there and look. Let me now discuss the Deep Space Network itself, because this is one of the most remarkable pieces of infrastructure ever built, and without it, Voyager would have been lost decades ago. The Deep Space Network consists of 3 facilities, roughly equally spaced around the Earth. One is in Goldston, California, in the Mojave Desert. One is near Madrid, Spain. One is near Canberra, Australia. This spacing ensures that at least one facility can communicate with a distant spacecraft at any time, regardless of Earth's rotation. Each facility has multiple large dish antennas. The largest are 70 meters in diameter, about the size of a football field. These enormous dishes collect the incredibly faint radio signals from spacecraft billions of kilometers away. They can also transmit powerful commands back to those spacecraft. The sensitivity of these antennas is almost unbelievable. They can detect signals as weak as 10 to the minus 16 watts, as I mentioned earlier. To put this in perspective, the total energy collected from Voyager's signal over the entire mission, all the data, all the images of Jupiter and Saturn and Uranus and Neptune, all the measurements of the interstellar medium, if you added up all the energy in all those signals over 46 years. It would not be enough to light a standard light bulb for 1 billionth of a second. Every piece of data we have from Voyager Every image, every measurement, every discovery came from signals weaker than the natural thermal noise in the receiver. The signal is literally buried in noise. Extracting it requires extremely precise knowledge of the signal's frequency, timing, and coding. This is done through a technique called phase coherent detection, where the receiver locks onto the extremely precise frequency of Voyager's transmitter, which is controlled by an onboard oscillator. By knowing exactly what frequency to look for, the receiver can integrate the signal over time, building it up above the noise floor. This is, in some ways, analogous to how you can hear someone whispering your name in a crowded room. The noise is much louder than the signal, but because you know what pattern to listen for, you can pick it out. The Deep Space Network knows the exact pattern of Voyager's signal, and it uses that knowledge to extract information from what would otherwise be indistinguishable from random noise, and here is another quantum connection. The fundamental sensitivity limit of the Deep Space Network is set by quantum fluctuations. At the quantum level, the electromagnetic field is never perfectly still. Even in the absence of any signal, the field fluctuates. These vacuum fluctuations set an absolute floor on the noise level of any receiver. No amount of cooling, shielding, or engineering can eliminate quantum noise. The Deep Space Network operates within a factor of a few of this quantum limit. We are essentially listening to the universe at the edge of what physics allows. I want to take a moment now to talk about something that connects everything we have discussed. The photon. The quantum of light. The messenger between Voyager and Earth. A photon is one of the strangest objects in physics. It has no mass. It always travels at the speed of light, approximately 300,000 kilometers per second. It cannot be slowed down or sped up. From the photon's own perspective, if we can even use that phrase, no time passes during its journey. Due to relativistic time dilation, at the speed of light, time stops completely. A photon emitted from Voyager and arriving at Earth 22 hours later, from our perspective, experiences zero elapsed time from its own perspective. This is worth pausing on. The photons carrying Voyager's signal experience no time during their journey. For them, the emission at Voyager and the absorption at Earth happen simultaneously. There is no travel. There is no journey. There is only departure and arrival, with nothing in between. Time for the photon does not exist. And yet, from our perspective, the photon crossed 24 billion kilometers in 22.5 hours. It existed. It travelled. It carried information. The discrepancy between these two perspectives is not a paradox. It is just the strangeness of relativistic physics. Time is not absolute. Different observers experience different amounts of time, and the photon is the extreme case, an observer for whom time does not flow at all. Every signal from Voyager is carried by these timeless messengers. They leave Voyager and, from their perspective, instantly arrive at Earth. From our perspective, they travel for nearly a day. This duality, this observer dependence of time, is one of the most profound insights of modern physics, and every time we download data from Voyager, we are making use of it. Let me now discuss the interstellar medium in more detail, because the space through which Voyager travels is far more interesting than the word empty suggests. The local interstellar medium, the specific region of interstellar space that our solar system is currently passing through, is a relatively warm and low-density region called the local interstellar cloud, or sometimes the local fluff. This cloud is about 30 light-years across and has a temperature of roughly 6,000 degrees Kelvin. That sounds hot, but remember, the density is incredibly low, about 1/10 of an atom per cubic centimetre. Temperature in physics refers to the average kinetic energy of particles, not to how hot something would feel. With so few particles, there is essentially no heat transfer. You would feel no warmth. You would feel nothing. The local interstellar cloud is itself embedded within a much larger structure called the local bubble, a region of very hot. very low-density gas that extends roughly 300 light-years around us. The local bubble was carved out by supernova explosions that occurred millions of years ago. These explosions swept up the normal interstellar gas into shells, leaving behind a cavity filled with extremely hot, million-degree plasma at incredibly low density. Our solar system has been travelling through the local bubble for several million years. At some point in the future, perhaps millions of years from now, the solar system will exit the local bubble and enter a region of denser, colder interstellar gas. This may affect the heliosphere, compressing it and potentially exposing Earth to more cosmic radiation. But this is far in the future. Voyager is currently in the local interstellar cloud, measuring its properties directly for the first time. The magnetic field, the plasma density, the temperature, the cosmic ray flux, all of these were unknown before Voyager reached them. We had models, predictions, estimates based on indirect observations. But Voyager gave us the ground truth, and as usual, reality was more interesting than the models. One unexpected finding was that the magnetic field in the local interstellar medium was stronger than predicted, and oriented differently than expected. This has implications for how the heliosphere interacts with the interstellar medium, and how cosmic rays are deflected before reaching the inner solar system. The magnetic field of the interstellar medium wraps around the heliosphere, shaping it like water flowing around a rock in a stream. Voyager also detected cosmic rays, high-energy particles, mostly protons and atomic nuclei, that have been accelerated to enormous energies by supernova shockwaves and other violent events elsewhere in the galaxy. Inside the heliosphere, the Sun's magnetic field partially shields us from these galactic cosmic rays. Outside the heliosphere, Voyager can measure the full, unshielded intensity of the cosmic ray background. This data is valuable for understanding the energy budget of the galaxy and the mechanisms that accelerate particles to such high energies. Some of these cosmic rays have energies that are truly astonishing. The highest energy cosmic ray ever detected, nicknamed the Oh My God particle, had an energy of about 300 million trillion electron volts, roughly the kinetic energy of a baseball thrown at 60 miles per hour, concentrated in a single subatomic particle. The origin of such ultra-high energy cosmic rays remains one of the great unsolved problems in astrophysics. They may come from the jets of active galactic nuclei, from gamma-ray bursts, or from some as yet unknown source. Voyager cannot detect such rare ultra-high energy particles. Its cosmic ray detectors are designed for lower energies, but it does measure the steady background of galactic cosmic rays at moderate energies, and this data helps us understand the overall cosmic ray spectrum and how it is affected by the heliosphere. Let me now take us to a topic that connects Voyager's loneliness to one of the biggest questions in science: the Fermi paradox. If the universe is so vast, if there are trillions of galaxies, each with billions of stars, many with planets, where is everyone? Why has no alien civilization ever contacted us? Why do we find no evidence of anyone else out there? This question is relevant to Voyager because Voyager is our farthest reach into the cosmos. It carries the golden record specifically in case someone finds it. But the odds are impossibly small, and the silence is deafening. There are many proposed solutions to the Fermi paradox. Perhaps intelligent life is far rarer than we assume. Perhaps civilizations tend to destroy themselves before they can become spacefaring. Perhaps the distances are simply too great for any civilization, no matter how advanced, to cross. Perhaps we are being observed but not contacted. Perhaps there is a great filter, some barrier that prevents civilizations from reaching a certain level of advancement. We do not know the answer. Voyager's silence as it travels through interstellar space, detecting no signals, no artifacts, no evidence of other intelligence, is data of a sort. Not conclusive, certainly. Voyager has barely left the driveway, as we keep saying. It has explored an infinitesimal fraction of even our own galaxy. Drawing conclusions from Voyager's lack of alien encounters would be like exploring a single grain of sand on a beach and concluding the beach is lifeless. but the silence is still haunting. And it connects to the quantum universe in an interesting way. One proposed explanation for the Fermi paradox involves the many worlds interpretation of quantum mechanics. In this interpretation, every quantum measurement causes the universe to branch into multiple versions, each realizing one possible outcome. If this is true, the total multiverse might contain civilizations everywhere, in some branches, but each individual branch might be relatively empty. We might be in a branch where nearby stars happen not to have produced intelligence. The apparent emptiness might be an artifact of which branch of the quantum multiverse we find ourselves in. This is highly speculative, of course. It is not testable, at least not with any technology we can currently imagine. But it illustrates how quantum physics permeates every level of our understanding of the cosmos, from the practical details of communication to the deepest existential questions about our place in the universe. Now, let me bring us to something more concrete and forward-looking. If Voyager represents the best we could do in 1977, what could we do today? What might we do in the future? How might we actually cross the driveway, leave the neighbourhood, and reach another star? The fundamental problem, as we have discussed, is distance. The nearest star is 4.2 light-years away. At Voyager's speed, that is a 73,000-year journey. Even at 10 times Voyager's speed, it would take 7,000 years. We need to go much, much faster. Chemical rockets, the kind that launched Voyager, are fundamentally limited by the energy density of chemical bonds. They can provide tremendous thrust for short periods, but cannot achieve anything close to the speeds needed for interstellar travel. We need entirely new propulsion concepts. One concept that has received serious attention is nuclear pulse propulsion. The idea, first studied in the 1950s under Project Orion, is to explode nuclear bombs behind a spacecraft, using the blast to push it forward. This sounds crude, and it is. But the energy density of nuclear reactions is millions of times higher than chemical reactions, so the achievable speeds are much greater. Estimates suggest a nuclear pulse vehicle could reach perhaps 5 to 10% of the speed of light. At 10% of light speed, the journey to Proxima Centauri would take about 42 years. Long, but within a human lifetime. Another concept is the solar sail, which uses the pressure of sunlight to accelerate a large, thin, reflective surface. Solar sails accelerate slowly but continuously, and they need no fuel. However, conventional solar sails become less effective as you move farther from the sun, so they are not well suited for interstellar distances. A much more promising variant is the laser sail. Instead of relying on sunlight, a powerful laser array on Earth or in orbit shines on the sail, pushing it to high speeds. The advantage is that the laser can be much brighter than sunlight and can continue pushing the sail for much longer. This is the concept behind Breakthrough Starshot, a research program announced in 2016 with funding from Russian-Israeli billionaire Yuri Milner. Breakthrough Starshot proposes building a massive ground-based laser array, perhaps 100 gigawatts, and using it to accelerate tiny spacecraft, each weighing just a few grams, with thin sails just a few meters across, to 20% of the speed of light. At that speed, the journey to Proxima Centauri would take about 20 years. A flyby mission, not an orbit, and the tiny spacecraft would have only seconds to collect data as they shoot past at 60,000 kilometers per second. But they would get there within a human generation. The engineering challenges are enormous. The laser array would need to be far more powerful than anything ever built. The sail material would need to withstand the enormous radiation pressure without melting or tearing. The spacecraft would need to be incredibly light while still carrying useful instruments and a communication system. The communication system would need to send data back from 4 light-years away using just a few watts of power. And here is where quantum technology might play a crucial role. At such low power levels, conventional radio communication would be impossibly slow, but optical communication, using laser light, could potentially work. the spacecraft could carry a small laser that transmits data back to Earth using individual photons. Detecting single photons from 4 light-years away would require telescopes and detectors at the absolute quantum limit of sensitivity. Future quantum communication technology, including quantum error correction codes and photon counting detectors operating at the quantum noise floor, might make this possible. We would literally be communicating across interstellar distances 1 photon at a time, each photon carrying 1 precious bit of information about an alien star system. This is not science fiction. This is active research. Engineers and physicists are working on each of these challenges right now. Whether it will succeed within our lifetimes is uncertain, but the fact that we are seriously working on it, that we have moved beyond dreaming and into engineering, is remarkable. And it all started with Voyager. Voyager proved that we could build machines that last decades in the harshness of space. It proved that we could navigate precisely across billions of kilometers. It proved that we could communicate across interstellar distances. It proved that the will to explore exists in our species at a deep, persistent level. Let me now discuss another aspect of Voyager's quantum connections that I find particularly beautiful: the quantum nature of the instruments themselves. Voyager carries several scientific instruments that rely directly on quantum physics for their operation. The cosmic ray subsystem uses solid-state detectors that work on quantum principles. When a high-energy particle enters the detector, it interacts with the semiconductor material and creates electron-hole pairs, tiny quantum events that produce an electrical signal proportional to the particle's energy. Without quantum mechanics, semiconductor physics would not work, and these detectors would be impossible. The magnetometer measures magnetic fields using a principle called the flux gate, which relies on the quantum mechanical phenomenon of magnetic domain behavior in ferromagnetic materials. The plasma wave system detects electric field fluctuations, each of which involves the collective quantum behavior of charged particles in a plasma. Even Voyager's clock, its timing reference for data transmission, is a crystal oscillator. The crystal vibrates at a precise frequency determined by its quantum mechanical lattice structure. The rigidity of the crystal, the frequency of vibration, the stability of the oscillation, all are consequences of quantum mechanics governing the bonds between atoms in the crystal. There is no part of Voyager that is not quantum mechanical at its foundation. Every transistor in its computer is a quantum device. Every solar cell on its calibration targets uses the photoelectric effect, which Einstein explained using quantum theory. The very metal of its structure has properties, strength, electrical conductivity, reflectivity, that are determined by quantum mechanics governing electron behavior in metals. We sometimes talk about quantum physics as if it belongs to the world of the very small, atoms and photons and electrons. But this is misleading. Quantum physics is the foundation of everything. It is the operating system of the universe. Everything else, chemistry, materials science, electronics, biology, is built on top of it. Voyager is as much a quantum machine as any particle in a laboratory. It is just that its quantum nature manifests in macroscopic, classical-looking behavior. The quantumness is hidden by decoherence, but it is there. Always there. Now let me address something that I think is important for understanding why the scale of space matters. Why it matters that Voyager has barely left the driveway. What does this fact teach us? It teaches us humility. Not the kind of humility that comes from feeling small and worthless, but the scientific humility that comes from recognizing how much we do not know, how much we have not explored, how much remains to be discovered. Consider this. If Voyager, after 46 years of travel, has explored 1/10,000th of the distance to the nearest star, and our galaxy contains hundreds of billions of stars, and the observable universe contains 2 trillion galaxies, then the fraction of the universe that humanity has directly explored is so small that there is literally no number in common use small enough to express it. We have explored nothing. We have seen nothing. We know almost nothing about what is actually out there. Everything we know about distant stars, galaxies, and the large-scale structure of the universe comes from light, from photons that happen to travel in our direction and land on our telescopes. We have never sent a probe beyond our solar system in any meaningful sense. We have never directly sampled the material of another star system. We have never observed a planet around another star with anything more than a few pixels of resolution. The universe is keeping its secrets, and it is keeping them not because they are hidden, but because we simply have not gone far enough to find them. This is the truth that Voyager's journey illuminates. The driveway is long, and we have barely started down it. Let me now talk about something that brings quantum physics and the cosmic scale together in a particularly striking way: the cosmic microwave background radiation. Voyager is bathed in the cosmic microwave background, the faint afterglow of the Big Bang. This radiation fills all of space uniformly. It was emitted about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. That light has been travelling for 13.8 billion years, stretching with the expansion of space from visible light to microwaves. The cosmic microwave background has a temperature of about 2.7 degrees above absolute zero. It is the most perfect black body spectrum ever measured. And its uniformity to about 1 part in 100,000 tells us that the early universe was extraordinarily smooth and homogeneous. But here is the quantum connection. Those tiny irregularities in the cosmic microwave background, the 1 part in 100,000 fluctuations, are believed to have originated as quantum fluctuations in the very early universe. During a period called cosmic inflation, which occurred within the first tiny fraction of a second after the Big Bang, the universe expanded exponentially rapidly. Quantum fluctuations, which normally exist only at subatomic scales, were stretched by this expansion to astronomical sizes. These stretched quantum fluctuations became the seeds of all structure in the universe. Every galaxy, every star, every planet, every atom in Voyager exists because of quantum fluctuations in the first instant of the universe. Think about that. The quantum fluctuations that created the seeds of cosmic structure are the same kind of fluctuations that exist in the vacuum right now. The same quantum uncertainty that governs the behaviour of individual photons and electrons. The entire large-scale structure of the universe, all the galaxies and clusters and voids, grew from quantum seeds. Voyager exists because of quantum mechanics in this deepest possible sense. Not just because its instruments use quantum effects. Not just because its power comes from quantum tunnelling. But because the very matter it is made of, the very star system it came from, the very galaxy it inhabits, all grew from primordial quantum fluctuations. Quantum mechanics is not just the physics of the small, it is the origin of the large. This brings us to another profound question. Is the universe fundamentally quantum? Is the classical world we see around us just an approximation, a coarse-grained view of an underlying quantum reality? The answer, as far as modern physics can tell, is yes. At the most fundamental level, everything is quantum. The classical world emerges from quantum mechanics through decoherence and the large number of particles involved. But the underlying reality, to the extent we can speak of such a thing, is quantum. This means that Voyager, as it drifts through interstellar space, is existing in a quantum universe. The space around it is a quantum field. The time it experiences is at some fundamental level quantum. The matter it is made of obeys quantum rules. The forces that hold it together are quantum. It is quantum all the way down. And yet, it is also unmistakably classical. It has a definite position, a definite velocity, a definite shape. It does not tunnel through things. It does not exist in superposition. The quantum and classical coexist in Voyager, just as they coexist in everything. The mystery of how one gives rise to the other, the measurement problem, the interpretation of quantum mechanics, remains unsolved. Voyager lives with that mystery, as do we all. Let me now take a slightly different angle and talk about the information that Voyager has sent back and what it means in the context of information theory and quantum information. Over its mission, Voyager has transmitted an enormous amount of data back to Earth. Tens of thousands of images, millions of measurements, decades of continuous monitoring of the interstellar environment. All of this information was encoded in radio photons and beamed across space. In classical information theory, developed by Claude Shannon in the 1940s, information is measured in bits. A bit is the fundamental unit of information, a choice between 0 and 1, yes or no, on or off. Every image Voyager sent, every measurement it made, was ultimately encoded as a sequence of bits and transmitted as a modulated radio signal. Voyager transmits data at a rate of about 160 bits per second. That is extraordinarily slow by modern standards. Your internet connection is probably millions of times faster. But remember, Voyager is transmitting from 24 billion kilometers away with a 23-watt transmitter. 160 bits per second from that distance is a remarkable achievement. Now, in quantum information theory, the fundamental unit is the qubit. A qubit can exist in a superposition of 0 and 1 simultaneously. It can be entangled with other qubits. It can carry more information per particle than a classical bit. Quantum communication protocols can, in principle, transmit information more efficiently than classical protocols, particularly in regimes where the signal is very weak and photons are scarce. For Voyager's situation, where we are dealing with an incredibly weak signal and need to extract maximum information from minimum energy, quantum information theory suggests we are not yet at the theoretical maximum efficiency. Future deep space missions might use quantum encoding and quantum receivers to push closer to the ultimate quantum limits of communication. The Holivo bound, a theorem in quantum information theory, tells us the maximum amount of classical information that can be extracted from a quantum system. For the photons arriving from Voyager, we are not yet at the Holivo bound. There is room in principle to do better. This is one of the active areas of research in quantum communication. How do you communicate optimally when photons are scarce? How do you encode and decode information at the quantum limit? Voyager itself will not benefit from these advances, but future missions, perhaps missions to other star systems, might rely on quantum optimal communication to maintain contact across light years. Let me shift now to discuss something else about Voyager that is scientifically fascinating: the radiation environment of interstellar space and what it means for the spacecraft's long-term survival. Interstellar space is permeated by cosmic rays, high-energy particles that zip through the void at nearly the speed of light. These particles come from supernova remnants, active galactic nuclei, and other violent astrophysical events. When a cosmic ray strikes a piece of electronics, it can flip a bit in memory, damage a circuit, or cause a malfunction. This is called a single event upset, or a single event effect. Voyager's electronics were built in the 1970s using older technology that is, interestingly, somewhat more resistant to radiation than modern microchips. Modern chips have transistors measured in nanometers, packed so densely that a single cosmic ray can affect multiple circuits simultaneously. Voyager's chips have much larger features, making them inherently more robust. This is one of the advantages of old technology in space. Nevertheless, over 46 years, the cumulative radiation damage has taken its toll. The memory chip failure that caused the 2023 communication crisis is likely a result of decades of cosmic ray bombardment. As Voyager continues its journey, more chips will fail, more systems will degrade. The spacecraft is slowly being worn away by the invisible rain of cosmic particles. This is also a quantum phenomenon. When a cosmic ray proton hits an atom in a silicon chip, the interaction is governed by quantum mechanics. The proton scatters off the atomic nucleus through the strong nuclear force. It can knock atoms out of their lattice positions, creating defects. It can ionize atoms, creating free charges that disrupt electronic signals. Each interaction is a quantum event, governed by probability amplitudes and cross-sections calculated from quantum chromodynamics and quantum electrodynamics. Voyager is being eroded by quantum events. One particle at a time, one interaction at a time, the cosmos is slowly reclaiming the matter that we assembled into a spacecraft and flung outward. Eventually, over millions and billions of years, cosmic rays and interstellar dust particles will completely destroy Voyager. Its atoms will be scattered back into the interstellar medium. It will become part of the raw material for future stars and planets. But that is a very long time from now. For the immediate future, the more pressing concern is power. As I mentioned earlier, Voyager's RTGs are losing about 4 watts per year. Each year, the engineering team has to decide which instruments and systems to keep running and which to shut down. They have already turned off the cameras, the spectrometers, the photopolarimeter. What remains are the instruments that can study the interstellar environment, the magnetic field, the plasma, the cosmic rays. The decisions about what to shut down are not just technical. They are emotional. Each instrument represents decades of work by scientists who dedicated their careers to the data it produces. Shutting down an instrument is like saying goodbye to a part of the mission. It is a slow farewell, stretched over years, as one by one the instruments go dark. By 2030, possibly sooner, the last instrument will be turned off. Sometime after that, the transmitter will no longer have enough power to function. Voyager will make its final transmission. Someone at JPL will record the moment. There may be a ceremony. And then there will be silence. After that, Voyager becomes a monument, a time capsule, a message in a bottle. It will carry the golden record through the darkness forever, but no one will be listening to it. No one will be talking to it. It will be alone in a way that no human creation has ever been alone before. Let me now talk about the other Voyager, Voyager 2, because it has its own story, its own journey, its own destination. Voyager 2 is heading in a different direction than Voyager 1. While Voyager 1 is heading roughly toward the constellation Ophiuchus, Voyager 2 is heading toward the constellation Sagittarius. They are diverging, getting farther apart from each other with every passing year. Voyager 2 crossed the heliopause in 2018, confirming that the heliosphere is a real, measurable structure and that you can exit it. But Voyager 2's crossing was different from Voyager 1's in important ways. The heliopause was farther out in Voyager 2's direction, suggesting the heliosphere is not symmetric. The conditions at the boundary were different. The plasma measurements, which Voyager 2 could make but Voyager 1 could not, revealed details about the temperature and speed of the plasma at the boundary. Voyager 2 also has a different future trajectory. In about 40,000 years, it will pass within about 1.7 light-years of Ross 248, a red dwarf star in the constellation Andromeda. In about 296,000 years, it will pass within about 4.3 light-years of Sirius, the brightest star in our sky. These are close passages, cosmically speaking, but still far too distant for any interaction. Both Voyagers will eventually be lost. Not destroyed necessarily, but lost in the sense that no one will know where they are. Without power to transmit, without any means of detection, they will become invisible. Two tiny human-made objects in an infinite void, unless someone finds them. And that brings us back to the golden record. The message, the hope. Carl Sagan knew the odds. He knew that the chance of the golden record ever being found was essentially zero, but he also knew that the act of creating the record, of choosing what to put on it, of deciding how to represent humanity to the cosmos was valuable in itself. It forced us to think about who we are, what matters to us, what we would want to say if we could only say one thing. The record contains 116 images. They include mathematical definitions, the location of our solar system relative to known pulsars, diagrams of human anatomy, photographs of landscapes and cities, images of food and architecture and nature. The audio portion includes greetings in 55 languages, starting with Sumerian, one of the oldest known languages, and including modern languages from every continent.